Welcome to the Explainer. Okay, let's jump straight into this. Today we're diving into the fascinating and honestly pretty dramatic world of chemistry. Now, I know exactly what some of you are thinking. Dry formulas, boring equations, endless memorization, right? Well, scratch that. We're going to completely reframe all of it today. We aren't just staring at random letters and numbers. We are literally going to witness a thrilling, microscopic social drama. Think of it like the ultimate reality show, where elements meet, fall in love, go through messy breakups, and, yeah, even steal each other's partners.
But before we start mapping out all these intense relationship dynamics, I've got to ask you a quick question. What is your Josh meter at today? If you're not familiar, in Hindi, Josh means enthusiasm, energy, passion. And to really grasp the beauty of these chemical reactions, our energy needs to be high. So check that Josh meter, get focused, and let's bring some serious energy to this explainer. So here's our game plan. First, physical versus chemical changes. Second, balancing chemical equations. Third, combination and decomposition. Fourth, displacement and double displacement. And finally, understanding redox reactions. Let's get into it.
Part 1. Physical versus chemical changes. Before we even talk about chemical reactions, we have to establish what a change actually means in science. Think of a physical change like an element just changing its outfit. If you melt an ice cube, sure, it turns into liquid water, but it's still H2O at the end of the day. If you tear a piece of paper, it's just smaller pieces of paper. Its core identity is totally intact. But a chemical change, that's a complete foundational transformation of identity. If you burn that exact same piece of paper, it turns into ash and gas. It is literally no longer paper. Or if iron rusts, it combines with oxygen and becomes a completely new compound. The actual chemical properties have shifted entirely.
Moving on to Part 2, balancing chemical equations. When elements interact and change identities, they have to follow a very strict universal rule. Everything has to stay perfectly balanced. And it all comes down to the law of conservation of mass, which tells us that mass can neither be created nor be destroyed. In the context of our chemical drama, this means you can't just magically spawn new atoms out of thin air, and you definitely can't make them vanish. Whatever elements enter a relationship on the left side of our equation, which we call the reactants, must perfectly equal the elements that exit on the right side, the products.
So how do we keep things fair? We use a super simple three-step table method. Step 1, you count up the number of atoms for each element on the reactant side. Step 2, you just do the exact same thing for the product side. And then step 3, this is where the magic happens, you multiply the entire compounds by numbers, known as coefficients, until both sides match up perfectly. It's really just a matter of tweaking those numbers until the scales are totally balanced.
Part 3. Combination and decomposition. Okay, now let's get into the actual relationship dynamics. We're looking at the first two major types of reactions, coming together and breaking apart.
First up is the combination reaction. This is basically the happy ending of our chemical drama. Two or more separate elements, our reactants, meet, fall in love, and combine to form one single unified product. A brilliant example of this is taking a piece of magnesium ribbon and burning it in oxygen. The magnesium and oxygen happily get together, and they celebrate by burning with this massive, dazzling white flame. And what's left behind? A brand new, single product, white magnesium oxide powder.
But, as we all know, not all relationships last. Which brings us to the decomposition reaction. This is the messy breakup. A single compound is essentially forced to break down into two or more separate products. And the absolutely crucial thing to notice here is why it happens. It's usually because of an external stressor. It takes actual energy to break a bond, specifically things like intense heat, electricity, or sunlight to force these elements apart.
Let's actually trace a breakup caused by heat, a thermal decomposition. Imagine heating up ferric sulfate crystals. At 0 seconds, these crystals are a vibrant, happy green color because they're bonded with water molecules. But as we crank up the heat, around the 10-second mark, that water evaporates away. The ferric sulfate is left all alone, its color completely drains out, turning a pale white. Finally, at 30 seconds, under that continued intense heat, the compound completely shatters. It decomposes into strong-smelling sulfur gases and a reddish-brown solid called ferric oxide. You are literally watching the relationship break down through these changing colors. Now, another way to force a breakup is through electricity, like when we split water into hydrogen and oxygen. To remember which gas goes where during this electrical breakup, there's a fantastic, cheeky Hindi phrase, chal hatoi, which roughly translates to, hey, move out of the way. It's an incredible memory tool. The C in CHAL stands for cathode, and HAT starts with H, which reminds us that hydrogen gas gathers at the cathode. Then OI starts with O, and the A sound in OI reminds us that oxygen gathers at the anode. Just a brilliant little trick to lock that knowledge in, for sure.
All right, part 4, displacement and double displacement. We've seen them come together, we've seen them break apart. Now let's move to the most dramatic reactions of the whole show, the steals and the mutual swaps. To figure out who steals from whom, we have to look at the hierarchy of power, known as the reactivity series. Elements higher up on this list are stronger, they're more reactive, which means they literally have the power to kick out lower elements and steal their partners. Our source material shares an absolutely legendary Hindi mnemonic to memorize this exact order, using cars and a Bollywood actress. Katrina Nakar mangi Alto Zen Ferrari, phir bhi hai kyo mili silver Audi. This translates to, Katrina asked for an Alto Zen and Ferrari car, but why did she get a silver Audi? If you look at the letters, K is potassium, Na is sodium, Ca is calcium, going all the way down to silver and Au for gold. It perfectly maps out the most powerful elements at the top down to the weakest at the bottom.
Let's see this power dynamic in action with a single displacement reaction. Imagine dropping iron into a beautiful clear blue solution of copper sulfate. Now think back to our mnemonic. Iron, the Ferrari, is much higher on the list than copper. So what happens? Iron flexes its muscles, kicks copper right out of the compound, and steals the sulfate partner for itself. Because of this, the product becomes iron sulfate, and the entire liquid dramatically shifts from blue to a pale green. And poor, weak copper, left completely alone, solidifying on the outside.
But what if two compounds just decide to mutually trade? That's a double displacement reaction. The source uses a brilliant IPL cricket analogy here. Imagine two pairs of friends. In pair 1, barium supports the RCB team, but his partner chloride supports CSK. In pair 2, sodium supports CSK, and sulfate supports RCB. It's a bit awkward, right? So during the match, they realize it makes way more sense to just sit with their fellow fans. They agree to a mutual swap. Barium leaves chloride to team up with sulfate, and sodium teams up with chloride. The ions perfectly swap partners, creating two brand new compounds, zero drama, zero fighting.
And this actually gives us a really important visual cue. Often, when these mutual double displacement swaps happen in a liquid, one of the brand new compounds that forms isn't soluble in water anymore. This solid residue that settles at the bottom is called a precipitate. For example, when barium and sulfate formed their new team in our last scenario, they instantly created this thick, white, insoluble solid that just sinks right to the bottom of the test tube.
Finally, part 5, understanding redox reactions. We are entering our final section, and this is arguably the most important give-and-take dynamic in all of chemistry. First things first, let's get our definitions straight. The word redox is really just a mashup of two words, reduction and oxidation. Oxidation simply means an element is gaining an oxygen partner. It's taking it in. Reduction, on the flip side, means an element is losing its oxygen partner. It's being stripped away. In a redox reaction, both of these things are happening at the exact same time. One element loses an oxygen, and another element swoops in and scoops it right up. Now here's the thing. Tests love to trick you by asking you to identify the agents in these reactions. Who's the oxidizing agent and who's the reducing agent? Well, there's a totally fail-proof method for this. From the source, the Akshay Kumar swipe trick. You literally just flip the terms. The substance that gets reduced is the oxidizing agent, and the substance that gets oxidized is the reducing agent. Why does this work? Because the guy who loses his oxygen, the one who gets reduced, is the very agent that provided the oxygen for the other guy to get oxidized. Just swipe and flip the terms, and I promise you'll never get it wrong.
To wrap up this explainer, I want to leave you with a direct challenge from our source material. It's a great way to test your active recall. We talked about splitting water using electricity earlier, right? We know the chemical formula for water is H2O, which means the ratio of hydrogen gas to oxygen gas by volume is 2:1. But think critically about this for a second. What is their ratio by mass? Take a moment, think about the atomic weights of hydrogen and oxygen, and see if you can solve the puzzle. It's a fantastic way to solidify everything we've talked about today. Thank you so much for joining me on this incredible journey through the social drama of chemistry, and hey, keep that Josh meter high.